Hello everyone, I welcome you all to this session of phase diagrams and phase transformations in ceramic systems. This is lecture 3.2. In the previous lecture, we discussed about the different types of compounds, and if we see a congruently melting compound and incongruently melting compound and compounds which undergo dissociation, by looking at the phase diagram, we understood that how to recognize those compounds. Okay, and the characteristics of those compounds, if I want to recap a bit. So first one is the congruently melting compound, which melts at a higher temperature and it becomes liquid, and if you are at lower temperature, it divides the phase diagram into multiple subdiagrams. However, if you see an incongruently melting compound which undergoes a peritectic reaction and transforms into a liquid and another solid, and the compounds can also dissociate. They can dissociate at a higher temperature, becomes two solids. They can dissociate at a lower temperature, become two solids, and the compounds can have both high temperature as well as low temperature dissociation characteristics. It means the compounds can be stable only up to a particular temperature range. Okay, by looking at all this, I would like to solve certain examples. In that, we'll try to construct these complex phase diagrams. Given a lot of information about the peritectic reactions, eutectic reactions and various different compounds, so how do I draw it? Okay, so that's we are going to discuss in the today's lecture. So let's talk about the construction of the Na and Bi phase diagram. Okay, sodium and bismuth phase diagram. So whatever the information is given, whenever you see this kind of problems, you just search for what are the information which is given, mainly the melting points, the decomposition temperatures, the stability regimes, and what are the other points like a two-phase stability, or what are the invariant reactions which is given. Some information sometimes it is missing. That's where you have to take some intelligent decisions, and those decisions are always comply with the phase rule requirements. What do you mean by that? It means at a point, say at a eutectic point, I should make the phase diagram in such a way that at eutectic point I should always get F is equal to 0. Or at a point where a compound melts congruently, F is equal to 0. Or a point where the compound dissociates into two solids, F has to be 0. Understand? So all these things, if the information is missing, then you have to take certain decisions, and those decisions should not violate the Gibbs phase rule. Okay, now let's start with the first example. Let's write everything very nicely, and step by step I'll teach you how to draw a phase diagram given the information. Okay, and if the information, certain aspects are missing, then how to predict those, that we are going to discuss in this lecture. Now, sodium and bismuth binary phase diagram we are going to draw today. Okay, the information is given in this way. Ni3Bi melts at 790 degrees Celsius, while NaBi decomposes at 450 degrees Celsius into Na3Bi and a liquid. So two different information is given here. The first information is Na3Bi melts at 790. What does it mean? Na3Bi, the moment I say Na3Bi, I am fixing the composition. What is the composition here? Na is to Bi is 3 is to 1. That composition is fixed. So fixed composition means it's a compound. So Na3Bi is a compound. It's a binary compound because it involves two components, and it melts at 790 degrees Celsius. It means at 791 degrees Celsius, what is stable? Liquid. And at, I know your 699, what is stable? At around at exactly 790, what is stable? Liquid as well as Na3Bi. Or any temperature below 790 degrees from this information, whatever information is given, what is stable? Na3Bi solid is stable. Okay, now let's go a little further. The eutectic temperatures are 97 degrees Celsius and 273 degrees Celsius. We'll use this information. Using this information, sketch the NaBi phase diagram where data is not provided. Sometimes some data is not provided. Okay, then you have to assume reasonable values wherever the data is missing. Okay, which the values which are assumed have to be consistent with the phase rule. Okay, what are the given things here? There are two compounds. One is NaBi and second one is Na3Bi. And eutectic temperatures are 97 degrees Celsius and 273 degrees Celsius. Now, melting point. Na3Bi is 790 degrees Celsius and the decomposition temperature of NaBi is given, that is 450, and it decomposes into Na3Bi as well as liquid. It decomposes into Na3Bi as well as liquid. So let's analyze. The analysis is the binary intermediate compound, a lime compound, has a fixed composition. Let's assume that the composition is X is to Y, where A and B are Na and Bi in this example. Okay. Now, atomic fraction of B in AXBY is what? Y divided by X plus Y, atomic percentage. So that's the reason I have multiplied with 100. Okay. Now, for NaBi, what is the percentage of Bi here? 1 divided by, Bi is 1 divided by X plus Y, 1 plus 1 into 100, it is 50% Bi. So where this compound is located? This compound is located at the midway, that is 50% Bi. If I draw Bi axis, I can also draw Na axis. It is not hard and fast rule that you should always draw Bi axis. No, you can also draw Na axis. Okay, you can draw Na on the left axis and Bi on the right axis, or vice versa. It depends on the convenience. Okay, and the simple equation which gives the percentage of the constituents, in this it is Na and Bi, it is given in this way. Okay. For NaBi, the fractions I have simply written in terms of fractions, divided by 100 you will get 0.5, and Na3Bi, the fraction of Bi is 2.25, is 25%. Okay. Now, Na3Bi melts at 790 degrees Celsius. I mentioned that it congruently melts. If the word congruently is not used, still you can use it as a congruently, you can consider it as a congruently melting compound. Why? Because at 790 when it melts, it transforms into liquid completely. Understand? So that's an invariant point, it's a melting point, and it's a compound, it has a unique melting point, same as that of its both Na and Bi respectively. Okay. Now, you have a congruently melting compound, that is Na3Bi, which melts at 790 degrees Celsius, and you have an incongruently melting compound. Why? Because in the problem it is given that, in the problem statement it is given that decomposition of NaBi takes place at 450 and it decomposes into one solid, that's a compound, Na3Bi, and a liquid. They are actually talking about peritectic reaction. It means 450 degrees Celsius with 50% of Bi. 50% equimolar composition is an invariant point, because composition is fixed, that is 50%, and the temperature is also fixed, and it undergoes and it shows a reaction where one solid gives one liquid and another solid. So that's the reason NaBi is an incongruently melting compound. Okay. Now eutectic temperatures are given, that is 97 degrees Celsius and 273 degrees Celsius. Two eutectics are given. It means the entire phase diagram is divided into sub-diagrams, and the sub-diagrams have eutectic invariance. Understand? Eutectic invariant reactions or invariant points. And the temperatures are given 97 degrees Celsius and 273 degrees Celsius. Okay. Now, let's draw it. So, for convenience, I am simply drawing Na on the left axis and Bi on the right axis. But it is not always true. You can also draw bismuth on the left axis and sodium on the right axis. That's also possible. Okay. Now, the first and foremost thing is to locate the compounds, because we already calculated the fraction of Bi which is required to locate Na3Bi and NaBi. Okay. This is Na3Bi, and it is to be drawn up to a point where you reach 790 degrees Celsius, because Na3Bi melts at 790. Understand? Now, NaBi, which decomposes at 450 into liquid and Na3Bi, it means the stability region is 450 degrees up to 450 degrees Celsius or any temperature below 450. Since this is not drawn exactly with a scale, so I am just showing the hypothetical, the quantitative diagram. Okay. So that's the reason you may feel that okay, you up to which is 450 and how come 790 is so near? No, I am not. It is not to the scale. Okay. Now, since it melts congruently, so above which you have only pure liquid, so I have drawn the liquidus cap. The liquidus cap, because above that you have pure liquid, because this melts congruently. However, NaBi decomposes incongruently. Understand? In that case, I have to secure a two-phase region here. This is the two-phase region. The liquidus profile has to be extended up to this point. Why? I cannot join this point here. The moment I join this point here, it means above this compound there exists a liquid. Then this becomes a congruently melting compound. That's a wrong diagram. Understand? And in addition to that, this cannot terminate somewhere here. Why? Because again NaBi, above NaBi I will get the liquid and it becomes a congruently melting system. But in the statement of the problem, it is given that NaBi doesn't melt, rather it undergoes decomposition into one more solid and a liquid. That's the reason I have secured this part. Now I can introduce an eutectic here. Since what is missing in the problem? The missing element in the problem was 273 degree. They said that it's an eutectic point, but they did not mention what composition it has. So our obligation is to maintain a fixed composition because it's an invariant point, but I don't have to worry about the location as such. So here, for simplicity, I am just taking an invariant reaction here, and that is to be located at 273. And here also I have two solids, and my liquidus cannot be terminated somewhere here because liquid cannot be stable at very low temperatures. Liquid is always stable at high temperatures. So I have to have another invariant reaction where the output should be solid. That is your eutectic point. So I am introducing one more eutectic here, that is 97. Again, the composition is not given, so I don't have to worry about the composition. If the composition is given, then I have to just tweak the position of the eutectic. But here my obligation is to maintain a fixed composition because I know that eutectic point is a fixed composition and fixed temperature point. It's an invariant point. Okay. Now I secure my phase fields and I locate the phase fields. Now you see this location. Let's start with this location. NaBi and Bi together they coexist here. So how do you decide that these two coexist? Just draw a tie line from here to here, and the tie line has to be drawn within the two phase region and it should terminate at single phase regions. Understand? Now NaBi is one phase, Bi is another phase. So if I draw a tie line here, so one end of the tie line is bismuth and another end of the tie line is NaBi compound, and it passes through the two phase region, and the two phase region has to be NaBi plus Bi. The same exercise you can do it here also. You draw an imaginary tie line here that connects Na3Bi and NaBi, and it passes through a two phase region of NaBi and Na3Bi. So that's the reason this has to be mentioned in this way. Understand? You can draw a tie line here also, so which connects single phase liquid and a single phase compound, that is NaBi, but it passes through NaBi plus L. So that's how we draw the phase diagram in this way. Okay. Let's go with another problem. This problem is slightly different and it is an interesting problem, so that's why I have included this. Consider MgSi system, magnesium and silicon binary system. Okay, and the fraction is represented in this way. Xmg plus Xsi is 1. It means Xmg, if I use anywhere in the problem, that is a fraction, that's not a percentage, and at constant temperature. Now, the melting points of pure magnesium and silicon are these two respectively. The interaction parameter is expressed in kilojoules per mole because it has same unit as that of enthalpy for a solid solution given in this way. I have just mentioned Xsi, so you can also express the whole equation in terms of Xmg. Understand? So I have just mentioned in this way. Now, the molar Gibbs free energy of the liquid phase is also given in this way. It is just simply your xi ln xsi plus xmg ln xmg. Okay, RT times that. Now, the molar Gibbs free energy of a congruently melting intermediate compound. Congruently melting intermediate compound. So congruently melting compound means it has got a fixed melting point, and that melting point you have two phase equilibria. Understand? And that compound is something, it looks something like this, MgMSiN. Understand? And this is the Gibbs free energy of the compound expressed as a function of temperature. Makes sense? Very good. Now, assume negligible terminal solid solubility. It means there is no solid solubility whatsoever. They are simple, diagrams. You do not have the end terminal solid solutions in this. Identify the stoichiometry of MgMSiN. It means I have to find out the values of M and N. It means I have to find out the chemical formula of the stoichiometry of this compound, congruently melting compound, and also determine its melting point and sketch the phase diagram based on this information, and also indicate any invariant reactions which are involved. Okay, now it's an interesting problem. Let's start with that. Now you have MgSi binary system. What is given? Expression of interaction parameter is given. Now the aim is to find out the stoichiometry. How will you find out the stoichiometry? The stoichiometry can be found from a simple math. The simple math is, so you see the interaction parameter which is expressed as this. The interaction parameter has to be negative or more negative, because congruently melting compounds generally they possess higher melting point. So interaction parameter is negative because there is an attraction between Mg and Si. So it is more negative. More negative is possible if this part of the equation is 0. Understand? So x, the 3x Si minus 1 whole square is 0. And in that case, I can find out the fraction of silicon, that is 1 by 3. And the fraction of Mg, because xSi plus xMg is equal to 1. So fraction of Mg is magnesium is 2 by 3. And magnesium is to silicon is 2 is to 1. So stoichiometry is Mg to Si. Very simple logic. Okay, we have used only one property, that omega, the interaction parameter, has to be negative. It is more negative for a compound. Now how do you determine the melting point then? At melting point, I know that there exists a phase equilibria, the two phase equilibria. It means the solid Mg2Si and the liquid of same composition are in equilibrium at melting point. So it means G of compound is G of L at melting point. So that is also both the functions are given, and if I substitute both the functions and I also determined what is xSi, I will just calculate GL here, and also I can calculate the G of the compound, and the melting point is the only one equation, one unknown kind of situation, and the melting point comes something like this, 1344 Kelvin. So the melting temperature of Mg2Si is 1344 Kelvin. Okay, so that's how we can use our basic understanding, basic thermodynamics, and the stability and the understanding of thermodynamic stability of these compounds. We can evaluate the stoichiometry, their melting point, and things like that. Okay, now how to draw it? I have again taken Mg on the left axis and Si on the right axis. There is no hard and fast rule that you should always take Mg on the x-axis. You can take Mg on the left axis. You can take Mg on the right axis as well. Okay. Now Mg2Si, I'll just mark it, and I know it is a congruently melting compound. It is mentioned in the problem statement, and it happens at 1344. It means above 1344 liquid is stable, means I have to put a liquid as cap. I put a liquid as cap. Now I cannot make liquid stable at low temperature. I have to have invariant reactions, two invariant reactions, such that the output of the invariant reaction should give two solids. So those are your eutectics. So that's how I have drawn this one, and simply I have marked all the two phase regions. Understand? Now how this two phase region is marked? Because Mg and Mg2Si, if I draw an imaginary tie line that terminates at two locations. So first location is Mg and second location is Mg2Si, and it passes through a two phase region like this. Okay. Now what are the invariant reactions involved? The invariant reactions involved are this: liquid gives the compound Mg2Si plus Si, and another liquid gives Mg2Si and Mg. So this is how we use the information to get we use the basic information, the thermodynamics as well as phase rule information, to find out the missing things in the diagram and just draw it. Okay. Now another problem I would like to solve. It's an interesting problem. So draw a hypothetical phase diagram between A and B that contains the following features. Means I have to draw a hypothetical diagram which contains the congruently melting compound, which contains an incongruently melting compound, a compound with UTLS, that is upper temperature dissociation, upper temperature limit of stability, and the diagram should also contain a compound which is lower temperature limit of stability, and it should contain eutectic and peritectic reactions, and also compounds with both upper and lower temperature limit of stability, and label all the phases. So the diagram, you can think the diagram may look little bit complex, but it is very easy to draw if you understand whatever we have discussed so far. Okay, now let's draw. I am just drawing C1 and C3, two compounds, and above C1 I have written liquid. It means it's a congruently melting compound. I have just drawn my liquidus profile. Why? Because at C1 melts at this point, it means it's a congruently melting compound. Above that you have liquid, and C3 I have to have one incongruently melting system also, incongruently melting compound also. So C3 I am locating somewhere here, because nothing is given as far as this compositions are concerned. So I just have to maintain the basic criteria, that is fixed composition. Understand? I am just maintaining that. Now C3 up to this point, above this you have a two-phase region. Above this still the liquidus is far. It means it's an incongruently melting system. I have completed the part of the phase diagram. The part of the phase diagram is what? You have L plus A, L plus C1. If you draw a tie line here, it terminates at C1 as well as single phase liquid. So it has to be L plus C1. Then C1 is a congruently melting compound and C3 is an incongruently melting compound. I have introduced two eutectic invariant points also. Now there are other things which are left. Okay. Now one compound I am showing it as C4. Okay, that has the upper temperature limit of stability. Upper temperature limit of stability, and it decomposes into C3 and B. Okay, now I can have another compound where, suppose C5 is a compound which undergoes dissociation at low temperature as well as high temperature. Low temperature as well as high temperature. So this compound C5 has both upper and lower temperature limits of stability. Okay, now I need one more compound which has only lower temperature limit of stability. That I can introduce here. I am introducing a compound where at higher temperature it decomposes into a liquid and one more solid. It means at higher temperature this C2 compound at higher temperature shows incongruency, but at lower temperature it decomposes into two solids, C3 and C1. Okay, so I have introduced the compound which is a lower temperature limit of stability, that is C2, and I have introduced another compound called C4 which has upper temperature limit of stability. I have introduced C5 which has both upper as well as lower temperature limit of stability. And if I mark all the phase fields, it looks like this. Since I have introduced two eutectics here, you can also introduce a peritectic here. There is no problem with that. There is absolutely no problem with that. You can introduce a peritectic here. So I can involve the peritectic reactions as well. So that's how we draw the complex phase diagrams with the given information. Thank you. Before to that, I have invariant reactions here. There are so many invariant reactions here. You have one liquid gives two solids, one liquid gives two solids here, and you have the compounds which undergo dissociation into multiple solids and a liquid and a solid. Okay, so I missed this point. So today's lecture is completed here, and we will discuss the further aspect in the next lecture. Thank you.